Imagine the vast, indifferent ocean stretching to an endless horizon. No land in sight, no compass, no maps, no phone signal, no GPS. Just you, your vessel, and the terrifying immensity of the sea. For millennia, this was the ultimate test of human ingenuity and courage. How did our ancestors, with nothing but their innate senses and an intimate knowledge of the cosmos, navigate these formidable waters? They read the stars like a celestial roadmap, felt the subtle currents, listened to the winds, and observed the flight of birds, unlocking secrets of direction from the natural world itself. Their survival hinged on a profound connection to their environment, a wisdom passed down through generations. Fast forward to today. We carry devices in our pockets that can pinpoint our exact location anywhere on Earth, with astonishing accuracy. A network of satellites orbits our planet, beaming down invisible signals that guide everything from supertankers to a solitary kayak. We live in an era of absolute digital certainty. But does this technological marvel truly make us better navigators? Or have we traded a deep, instinctual mastery for a reliance on silicon and code? This documentary, Ancient Stars versus Modern GPS, Who Navigated the Seas Better?, embarks on an epic voyage to answer that question. Across 24 immersive sections, we will delve into the breathtaking techniques of ancient Polynesian wayfinders and Viking explorers, dissect the science behind their stellar charts and wave patterns, and compare their methods with the intricate engineering of our modern global positioning systems. We will weigh the human spirit's raw resilience against the infallible precision of algorithms, exploring the triumphs, limitations, and ultimate legacies of both navigational eras. Prepare to rethink what it truly means to find your way. From the moment humanity first walked upright, an insatiable curiosity stirred within us. A primal whisper urged us to gaze beyond the horizon, to push past the known, to discover what lay on the other side of that distant mountain range, or across the shimmering expanse of a great river. This isn't merely a desire. It's a fundamental drive, etched into our very DNA, the irresistible urge to explore. For millennia, this instinct has been the engine of human progress, propelling us from nomadic hunter-gatherers across continents, populating every corner of the earth. But every journey, every venturing into the unknown, carries with it a profound, terrifying question. How do we find our way back? How do we even know where we are going? On land, early wayfinders relied on familiar landmarks, towering trees, distinctive rock formations, the meandering course of a river. They followed animal trails, learned the subtle shifts of the sun's arc, and memorized vast mental maps of their territories. Yet, a far greater challenge loomed, an expanse so vast, so featureless, that all terrestrial markers vanished into an endless blue, the open ocean. Here, the familiar rules dissolved. Here, without an anchor point, without a compass or a map, a vessel could drift hopelessly, swallowed by the immensity, its crew lost forever, to the silent, unforgiving, deep. But the allure of the unknown proved stronger than the fear of being lost. The promise of new lands, abundant resources, or simply the thrill of discovery, beckoned humanity onto the waves. This was the ultimate test of ingenuity, courage, and observation. To conquer the oceans, ancient mariners had to do more than build seaworthy vessels. They had to master an entirely new language of the world, one written not in stone, but in the fleeting patterns of water, wind, and the eternal, silent sweep of the cosmos above. This documentary begins our journey into that profound challenge, contrasting the ancient mastery of the stars with our modern reliance on satellites to ask, who truly navigated the seas better? Before sextants, before chronometers, before the very concept of latitude and longitude, humanity found its first, most universal map. It wasn't drawn on parchment or carved in stone. It was painted across the boundless canvas of the night sky. As our ancestors transitioned from land-based wayfinding to the perilous journey across open water, they began to recognize immutable patterns in the celestial dance above. The sun's predictable path by day, the moon's monthly cycle, and, most critically, the constant, unchanging positions of certain stars became their anchors in a world stripped bare of familiar landmarks. Every night, the same constellations would appear, wheeling slowly around a fixed point in the northern hemisphere. Polaris, the North Star, a steadfast beacon of true north. In the southern hemisphere, mariners learned to identify the Southern Cross, pointing towards the celestial South Pole. This celestial guide was not only constant, but also globally accessible, a shared reference point for wanderers from the Arctic to the equator. It was the first truly universal navigation system, available to anyone with keen eyes, and the patience to observe. Ancient astronomers, often the same individuals who would later become master navigators, spent lifetimes meticulously charting these celestial movements. They named the stars, wove mythologies around their patterns, and, in doing so, transformed a chaotic scattering of light into an organized, readable roadmap. For civilizations separated by vast oceans and centuries, the night sky offered a common language, a silent dialogue between humanity and the cosmos. It was the original GPS, if you will, a system of cosmic coordinates that, with practice, could tell you where you were going, and how to get there. It taught them not just direction, but time and season, allowing for the planting of crops, the timing of migrations, and crucially, the planning of voyages. The stars, unchanging and eternal, became the bedrock upon which all future navigation would be built, a silent promise of guidance in a world of infinite possibility. From the vast, star-dusted reaches of the Pacific Ocean emerged perhaps the most astounding navigators in human history, the Polynesians. Without metal instruments, without written charts in the European sense, they undertook epic voyages that would make modern sailors gasp, colonizing an oceanic territory larger than any continent, a triangle stretching from New Zealand to Easter Island to Hawaii. Their secret was not a single tool, but a profound, holistic understanding of their environment, meticulously passed down through generations of master navigators, or PWO. Central to their system was the star compass, a mental construct of 32 rhumb lines corresponding to the rising and setting points of key stars around the horizon. A navigator like Pialug, who revitalized traditional wayfinding in the late 20th century aboard the Hokulea, could hold this complex map in his mind, constantly orienting his canoe by remembering where specific stars would rise and set throughout the night. By day, they used the sun's position, cloud formations, and the subtle color shifts of the sky to maintain their course, but stars were only one part of their intricate tapestry of knowledge. Polynesian navigators were expert readers of ocean swells, not just the wind-driven waves, but the deeper, more consistent swells generated by distant storms and deflected by unseen islands. They could feel these patterns through the hull of their canoe, interpreting the way they intersected and refracted as clues to land masses far beyond the horizon. They observed the flight patterns of birds, knowing that certain species would fly out to sea in the morning to feed and return to land at night. They noted changes in cloud formations, the scent of land carried on the breeze, the presence of specific marine life, and the subtle variations in watercolor and temperature. Their canoes, like the famous double-hulled vessels capable of carrying dozens of people and provisions, were perfectly designed for these long voyages. The Polynesians didn't just sail the ocean, they sailed with it, becoming one with its rhythms. Their navigation was an art, a science, and a spiritual practice, a testament to human ingenuity and an intimate connection with the natural world that remains unparalleled, challenging our modern notions of what it means to truly navigate. Thousands of miles and centuries away from the sun-drenched Pacific, another formidable seafaring culture wrestled with the immense challenge of oceanic navigation, the Vikings. From the late 8th to the mid-11th centuries, these Norsemen launched their iconic longships into the treacherous, often fog-bound waters of the North Atlantic, venturing from Scandinavia to Iceland, Greenland, and ultimately, North America, nearly 500 years before Columbus. Their feats of exploration, immortalized in sagas, are all the more remarkable given the notoriously difficult conditions they faced. Unlike the Polynesians, who often enjoyed clear, equatorial skies, Viking mariners frequently battled overcast weather, persistent fog, and the long, sunless winters of the northern latitudes. Direct stellar observation was often impossible, yet they too possessed an intimate, generational understanding of their environment. They keenly observed the migration patterns of birds, the color of the sea, the shifts in ocean currents, and the behavior of whales, all offering clues to proximity of land or changes in the weather. When the sun was obscured, legend and archaeological evidence suggest they employed an ingenious tool, the sunstone. While its exact nature is debated, perhaps a cordierite or calcite crystal, sagas describe a stone that, when held up to the sky, could polarize light, revealing the sun's position even through thick cloud cover or at twilight. This would have allowed them to determine direction with remarkable accuracy, even when the sun itself was hidden. They also possessed a rudimentary sun compass, a wooden disc with a central gnomon that cast a shadow, helping them maintain a bearing on clear days. Their navigation was a blend of courage, brute force, keen observation, and groundbreaking innovation. Leif Erikson's voyage to Vinland around 1000 AD, a testament to their skill, relied on a mixture of coastal piloting, celestial observation when possible, and a profound instinct for the sea. The Vikings, masters of raiding and trade, were first and foremost masters of the unforgiving northern seas, their methods a stark contrast to their Pacific counterparts, yet equally effective in conquering the vastness of their world. As the Roman Empire waned, a new golden age of scholarship and exploration bloomed in the Islamic world. From the 8th to the 14th centuries, Arabian astronomers and navigators became the undisputed masters of celestial precision, building upon the knowledge of Greek, Indian, and Persian civilizations. While Polynesians navigated by instinct and Vikings by ingenuity, the Arab world brought unparalleled scientific rigor to the art of wayfinding, transforming it into a precise science of calculation and instrumentation. Their vast maritime trade routes, stretching from East Africa to China, demanded accuracy. Merchants and explorers needed not just to find their way, but to do so efficiently and predictably across thousands of miles of open sea, often navigating by the fixed stars for weeks on end. It was in this environment that instruments like the astrolabe truly flourished. Though its origins were Hellenistic, Arabian scholars meticulously refined the astrolabe, making it a portable, sophisticated analog computer capable of calculating the time, measuring the altitude of celestial bodies, and determining latitude. Beyond the astrolabe, they developed detailed star charts and astronomical tables, the zyges, which cataloged the positions of thousands of stars with incredible accuracy for specific times and locations. Scholars like al-Battani and al-Biruni made crucial advancements in trigonometry and spherical astronomy, providing the mathematical backbone for these precise calculations. They also improved the quadrant, an instrument used for measuring angles, and utilized the kamal, a simple yet effective device for measuring the altitude of Polaris or the Sun to determine latitude. These advancements weren't confined to dusty observatories. Arabian navigators, the Pilo Mu'allim, translated this theoretical knowledge into practical oceanic guidance, meticulously recording their journeys and sharing their discoveries. Their meticulous approach, combining mathematical exactitude with sophisticated observational tools, laid essential groundwork for all future global navigation. They transformed the art of reading the stars into a science of measurement, charting a course that would eventually lead the world into an era of global interconnectedness. By the 15th century, the stage was set for an era of unprecedented global expansion, driven by European ambition and facilitated by the accumulated navigational knowledge of previous civilizations. The Age of Discovery, as it became known, saw European explorers combine the precision instruments of Arabian astronomers, the daring spirit of Viking mariners, and their own innovations to launch voyages that would forever redraw the map of the world. Fueled by desires for new trade routes to the east, access to lucrative spices and goods, and the expansion of empires in Christianity, figures like Vasco da Gama, Christopher Columbus, and Ferdinand Magellan embarked on journeys that defied the imagination. They sailed not just across seas, but around continents, proving the Earth was indeed a sphere and ushering in an era of global interconnectivity, albeit one often fraught with conflict and colonialism. These explorers utilized a suite of tools: magnetic compasses, perfected from Chinese designs, quadrants and astrolabes for celestial observation, drawing directly from Arabian advancements, and rudimentary portolan charts that grew increasingly accurate with each voyage. The development of more robust, ocean-going vessels, like the Portuguese caravel and the Spanish galleon, provided the platforms for these epic journeys. The challenge of calculating longitude, however, remained a persistent, deadly riddle, claiming countless ships and lives until the invention of the chronometer in the 18th century. Yet, despite these limitations, their ambition was boundless. In 1492, Columbus famously sailed west across the Atlantic, believing he could reach Asia. Less than 30 years later, Magellan's expedition achieved the first circumnavigation of the globe, a monumental feat of endurance in navigation that spanned 3 years, 1519 to 1522. These voyages were not just about finding new routes. They were about claiming new territories, spreading influence, and forever altering the course of human history. The European Age of Discovery stands as a testament to the power of human perseverance and the relentless pursuit of what lay beyond the horizon, synthesizing centuries of knowledge into a global endeavor that reshaped the world. While celestial navigation provided crucial fixed points, the altitude of a star or the sun-giving latitude, what did mariners do when the skies were obscured by weeks of unrelenting cloud cover, or when navigating through treacherous coastal waters where landmarks were hidden? This is where the venerable, often perilous, art of dead reckoning became paramount. Not a method for finding a definitive position, but rather for estimating it. Dead reckoning was a complementary ancient technique universally employed by navigators across cultures, allowing them to keep moving forward even when the stars were hidden. Dead reckoning is deceptively simple in concept. Knowing your last fixed position, you calculate your current estimated position by factoring in your speed, direction, and the time elapsed since that last fix. Imagine a navigator on a rolling deck, with a magnetic compass giving direction and a simple log line thrown overboard to estimate speed. The log line, knotted at regular intervals, would be trailed behind the ship. As it paid out, a sandglass would measure a fixed period, and by counting the knots that passed during that time, the navigator could estimate the ship's speed in knots, a term still used today. Every hour or watch, these readings would be diligently recorded in a logbook. The navigator would then plot this course and distance on a chart, literally drawing their path from the last known point. It was a continuous, iterative process, fraught with potential for error. Ocean currents could push the ship off course, unnoticed. Winds could subtly alter direction. Inaccurate speed estimations, a faulty compass, or simply human error in calculation could lead to increasingly significant deviations over time. Yet, despite its inherent inaccuracies, dead reckoning was absolutely essential. It was the navigator's best guess in the face of uncertainty, a lifeline when the heavens offered no guidance. It allowed ships to sail for days, sometimes weeks, without a celestial fix, always hoping for a break in the clouds to confirm or correct their estimated position. It was a testament to the human mind's capacity to build a coherent picture of reality from fragmented data, keeping the spirit of exploration alive even in the most challenging conditions. Ultimately, what binds these diverse narratives of ancient navigation together isn't merely the ingenuity of their tools or the boldness of their voyages. It's the profound, undeniable centrality of the human mind itself. Ancient navigation was not a mechanical process. It was a holistic art form, deeply reliant on the navigator's memory, observation skills, intuition, and an almost spiritual connection to their environment. Instruments were aids, but the true computer was the human brain, honed by years, often decades, of dedicated practice and inherited wisdom. Imagine the Polynesian PWO memorizing hundreds of star paths, the subtle nuances of dozens of swell patterns, and the behavioral traits of countless marine species. Or the Viking navigator, feeling the shifts in wind and current in his bones, interpreting the cry of a distant bird as a sign of land. Or the Arabian muallim not just reading an astrolabe, but internalizing the complex mathematics, understanding the deeper celestial mechanics it represented. These were not just individuals. They were living libraries of knowledge, their minds vast databases of environmental data, passed down orally, through apprenticeship, and through rigorous, lifelong learning. It was a constant process of observation, the color of the horizon at sunrise, the direction of a distant cloud, the scent carried on the breeze, the presence of specific fish or birds. These were all pieces of an intricate puzzle that only a trained, sensitive human mind could assemble into a coherent picture of position and direction. Mistakes were not just theoretical. They meant loss of life, starvation, or a tragic drift into the unknown. The pressure was immense, demanding unparalleled focus and an almost preternatural awareness of their surroundings. In our modern world, we rely on a different kind of oracle, the unwavering precision of satellites, constantly beaming down our exact location with breathtaking accuracy. We tap a screen, and a voice guides us. But in doing so, have we lost something profound? The ancient mariner's journey was not just a physical one across oceans, but an intellectual and spiritual voyage of deep engagement with the natural world. It was a testament to the pinnacle of human observational skill, memory, and an enduring bond between humanity and the grand guiding forces of the cosmos. A bond that perhaps we are only now beginning to truly appreciate. While the stars offered an ethereal compass, ancient navigation was a crucible of challenges, demanding unwavering dedication, profound knowledge, and often sheer luck. It was a practice fraught with limitations, its very ingenuity tethered to the whims of the natural world. Imagine spending months at sea, your only guide a handful of celestial bodies, meticulously plotting your course, using instruments that, while ingenious, were inherently prone to human error and environmental interference. This was a labor-intensive endeavor, requiring constant observation, calculation, and correction. The Polynesian navigators, for instance, learned to read swells and currents, a complex, intuitive knowledge passed down through generations. But even their mastery had limits. A clear night sky, an essential prerequisite for celestial observation, was a luxury, not a guarantee. The slightest cloud cover, a persistent fog, or the fury of a tempest could render the heavens invisible, plunging mariners into a terrifying blindness. Days, even weeks, could pass without a single star sighting, forcing crews to rely on dead reckoning, a method of estimating position based on speed, elapsed time, and direction. And here lay a critical vulnerability. Any small error in estimation, any unnoticed current, any misjudgment of speed would compound over time, leading to cumulative inaccuracies that could send a vessel hundreds of miles off course. Consider the consequences. An error in latitude calculation could mean missing a small island nation entirely, sailing endlessly into the featureless expanse of the open ocean. A miscalculation of longitude, notoriously difficult to determine before the invention of accurate chronometers, could leave a ship unable to gauge its east-west position with any reliability. Food and water provisions, meticulously calculated for a known journey, would dwindle to nothing. Sickness would spread. Hope would recede. The risks were not merely inconvenience, they were existential. Shipwrecks, starvation, and thirst were common fates for those who dared to challenge the ocean without flawless guidance. The knowledge held by these ancient mariners was hard-won, often paid for with the lives of their predecessors. It was a monumental human achievement, yes, but one carved from the very fabric of risk and uncertainty, forever at the mercy of the skies above and the unforgiving waters below. The ambition to traverse the globe was boundless, but the tools at hand, though wielded with incredible skill, imposed a heavy price for every mile gained. As the 20th century dawned, humanity's relentless pursuit of mastery over the seas took a dramatic turn, moving beyond the celestial sphere and towards an invisible frontier, the electromagnetic spectrum. The advent of radio technology, initially conceived for communication, rapidly revealed its revolutionary potential for navigation. No longer would mariners be solely beholden to the caprice of the weather or the clarity of the night sky. The very air itself, now pulsating with radio waves, offered a new, more reliable guide. This was the dawn of radio navigation, a pivotal precursor to the absolute precision we know today with GPS. Early radio beacons, established on coastlines, emitted signals that ships could pick up, allowing them to determine their bearing relative to the known beacon. Imagine a ship's radio operator, headphones clamped over his ears, listening for a distinct sequence of dots and dashes, Morse code, which, when properly interpreted, could provide a line of position. Cross-referencing signals from two or more beacons would then give a precise location on the chart. This was a monumental leap. No longer did a dense fog mean total blindness. Now, an electronic lifeline could pierce through the shroud, offering a sense of direction when visibility was zero. The true revolution, however, arrived with more sophisticated systems like LORAN, long-range navigation, developed during World War II. LORAN utilized chains of synchronized radio transmitters that broadcast pulses. A ship's receiver would measure the tiny time difference between receiving pulses from a master station and several secondary stations. These time differences translated into hyperbolic lines of position on specialized charts, and where these lines intersected, there was the ship's location. The accuracy, while not absolute, was unprecedented for its time, providing fixes within hundreds of feet or a few miles, even thousands of miles from shore. Crucially, LORAN operated 24/7 in all weather conditions, largely unaffected by the atmospheric disturbances that plagued visual and celestial methods. It marked a definitive shift, beginning to untether navigation from the direct, labor-intensive observation of nature, heralding an era where machines, not just men, would guide vessels across the vast, indifferent oceans. This invisible web of signals laid the foundational concept that timing, not just sighting, could unlock global positioning. The calm precision of radio navigation was about to be eclipsed by a far more ambitious, strategically vital endeavor born from the crucible of the Cold War. As the mid-20th century plunged the world into an ideological standoff, the stakes for military supremacy reached unprecedented heights. The Soviet Union's launch of Sputnik in 1957 sent shockwaves through the United States, sparking the space race and an urgent quest for technological dominance. It was in this atmosphere of intense global competition and existential threat that the seeds of GPS were sown. Military strategists desperately needed a foolproof way to track their assets: submarines stealthily patrolling the depths, strategic bombers traversing continents, and perhaps most critically, intercontinental ballistic missiles. Existing systems, including LORAN, while effective, lacked the universal accuracy and global coverage demanded by an increasingly interconnected and volatile battlefield. Imagine a nuclear submarine, a silent hunter beneath the waves, needing to know its precise location to launch a retaliatory strike with absolute certainty. Or a reconnaissance aircraft flying over enemy territory, requiring unparalleled positional data for its mission. This was not about finding your way to a port. It was about national security, about the balance of power, about survival itself. Inspired by the observation that Sputnik's radio signal shifted in frequency as it passed overhead, the Doppler effect, American scientists at Johns Hopkins Applied Physics Laboratory realized that if they could track Sputnik from a known location, they could also, conversely, track a receiver's location from a known satellite. This breakthrough led to the development of Transit, the U.S. Navy's first satellite navigation system, operational by 1964. Transit was revolutionary, but it only provided a positional fix every hour or so as satellites passed overhead. What was needed was continuous, global coverage in 3 dimensions: latitude, longitude, and altitude. The true genesis of what we now call GPS began in the early 1970s, with various military branches independently pursuing their own navigation solutions. Recognizing the inefficiency and potential for duplication, the Department of Defense consolidated these efforts into a single, unified program, the Navstar GPS, Navigation Signal Timing and Ranging Global Positioning System. Its mission was unambiguous: to provide highly accurate, continuous positioning, navigation, and timing information to military users worldwide, even in the most remote and hostile environments. This strategic imperative, forged in the fires of geopolitical tension, laid the groundwork for a technology that would, decades later, transform civilian life in unimaginable ways. But its initial purpose was clear: to win the Cold War. From its clandestine military origins, GPS has evolved into an astonishingly robust system, working silently above us, an invisible web that has redefined our relationship with location. But how does this seemingly magical technology pinpoint your exact spot on Earth with such uncanny accuracy? At its core, GPS is a triumph of physics and engineering, a complex ballet performed by a global constellation of satellites, ultra-precise atomic clocks, and the genius of triangulation. Imagine a network of at least 31 active satellites, each roughly the size of a small car, orbiting Earth at an altitude of approximately 2,200 kilometers, traveling at speeds of over 14,000 kilometers per hour. These satellites are not merely silent observers. They are broadcasting constant, precise signals. Each signal contains 2 crucial pieces of information: the exact time the signal was sent, and the precise orbital position of the satellite at that moment. And here's where the marvel of atomic clocks comes into play. Each satellite carries multiple atomic clocks, accurate to within a nanosecond, a billionth of a second, ensuring the timing information is extraordinarily precise. When your GPS receiver, be it in your smartphone, car, or a specialized device, picks up these signals, it performs a remarkable calculation. It compares the time a signal was sent by a satellite with the time it was received. The difference between these 2 times, multiplied by the speed of light, tells the receiver exactly how far away it is from that particular satellite. This is where triangulation, or more accurately, trilateration, comes into play. If your receiver can determine its distance from just one satellite, it knows it's somewhere on a sphere with that satellite at its center. With 2 satellites, it narrows its position down to a circle where the 2 spheres intersect. With a 3rd satellite, the receiver can pinpoint its location to one of 2 possible points on Earth. And with a 4th satellite, the system can not only confirm the exact location, but also calculate your altitude, providing a full 3-dimensional fix. This constant exchange of hyper-accurate timing data, from multiple satellites to your small receiver, creates an invisible web of information. It's a continuous, dynamic calculation happening millions of times a second, allowing your device to update your position in real time, whether you're navigating a bustling city street or exploring a remote wilderness. This intricate dance of physics, satellites, and atomic precision is the silent engine behind our modern sense of effortless navigation. The transition from ancient stargazing to modern satellite signals isn't merely a change in method, it's a leap into an entirely new dimension of accuracy and precision. Where ancient mariners might have been thrilled to land within sight of their destination after weeks at sea, modern GPS offers a level of positional certainty that was once unimaginable. For the average consumer, a standard GPS receiver can pinpoint a location to within a few meters, remarkable when you consider the signals are traveling over 20,000 kilometers from space. This meter-level accuracy has become the bedrock of daily life, guiding cars, tracking packages, and helping us find the nearest coffee shop. But for specialized applications, even meter-level precision isn't enough. Enter the world of differential GPS, or DGPS. This enhancement uses a network of fixed, ground-based reference stations at known, precisely surveyed locations. These stations receive GPS signals and compare their calculated position with their known true position. Any discrepancy is a measure of error in the GPS signal, errors caused by atmospheric conditions, satellite clock drift, or orbital inaccuracies. The reference station then broadcasts this correction data to DGPS-enabled receivers in the vicinity. With these real-time corrections, DGPS can achieve accuracy down to tens of centimeters, transforming numerous industries. Imagine the impact. In surveying, where painstaking measurements once took days, now a single DGPS unit can map vast tracts of land with unparalleled speed and precision. Construction projects, from skyscrapers to bridges, rely on DGPS to ensure foundations are laid and structures are erected to exact specifications. In agriculture, DGPS-guided tractors can plant seeds, apply fertilizer, and spray pesticides with centimeter-level precision, minimizing waste, optimizing yields, and reducing environmental impact, a concept known as precision agriculture. Even mapping, from creating highly detailed topographic maps to designing urban infrastructure, has been revolutionized. Beyond these, applications like geological fault monitoring, autonomous vehicle development, and even forensic accident reconstruction hinge on this extraordinary precision. The era of close enough is long past. With modern GPS, particularly its augmented forms, we operate in a world where a few centimeters can mean the difference between success and failure, a testament to how far humanity has come in mastering the art of knowing exactly where it stands. From the rarefied realm of military strategy and specialized industry, GPS embarked on its most profound journey yet, into the everyday lives of billions. What began as a tool for Cold War dominance was, by the turn of the millennium, becoming a ubiquitous companion, shrinking from refrigerator-sized ground stations to chips small enough to fit in the palm of your hand. This transformation ushered in an era of unparalleled convenience, making navigation effortless and accessible to virtually anyone with a modern device. Initially released for civilian use with selective availability, a deliberate degradation of accuracy for non-military users, this restriction was famously lifted by President Clinton in May 2000. Suddenly, the full precision of GPS was available to everyone, everywhere. The impact was immediate and profound. Dedicated GPS units, once bulky and expensive, became commonplace in vehicles, forever changing how we travel. No more fumbling with unfolding paper maps on a busy highway. No more arguments over directions. A calm, synthesized voice could guide you turn by turn to almost any address on Earth. But the true revolution came with the smartphone. The integration of miniature GPS receivers into mobile phones transformed them from communication devices into powerful navigational tools. Suddenly, the power to know precisely where you were and how to get where you needed to be was literally in your pocket. Walking directions, public transport information, ride-sharing services, even geotagging photos, all became possible, seamlessly interwoven into the fabric of daily existence. Today, GPS isn't just in our phones. It's embedded in our cars, our smartwatches, fitness trackers, drones, and countless IoT devices. Delivery drivers navigate complex routes with efficiency. Hikers venture into the wilderness with a reliable digital compass. Emergency services locate distress calls with unprecedented speed. The ability to track assets, manage logistics, and optimize routes has become fundamental to global commerce. We use GPS so instinctively now that we rarely stop to consider the staggering complexity behind its operation. It has become an invisible, expected utility, like electricity or water, an omnipresent digital compass that has largely eradicated the fear of being truly lost, profoundly reshaping our perception of distance and direction. The world, once vast and mysterious, has been digitally mapped and made instantly traversable, all thanks to those silent satellites circling high above. While GPS has undeniably transformed how we find our way, its profound influence extends far beyond mere navigation. Beneath the surface of our everyday experiences lies a deeper, often unseen web of critical applications that leverage GPS's unparalleled precision in timing and location. These are the unsung heroes of the modern world, silently underpinning infrastructure, safeguarding communities, and fueling scientific discovery. One of the most crucial, yet least visible roles of GPS is in providing ultra-precise timing. The atomic clocks aboard each satellite aren't just for calculating distances. They broadcast a global time standard accurate to nanoseconds. This precise timing is absolutely essential for synchronizing countless digital systems worldwide. Think of the global financial markets, where billions of dollars are exchanged every second. Every transaction, every trade, must be time-stamped with unimaginable accuracy to prevent fraud and ensure orderly operations. Without GPS timing, these complex networks would collapse into chaos. Power grids, telecommunications networks, and even the Internet itself rely on this synchronized heartbeat to function effectively and reliably. Beyond timing, GPS plays a vital, life-saving role in disaster response and emergency services. When earthquakes strike, wildfires rage, or hurricanes devastate coastlines, precise location data is paramount. Search and rescue teams use GPS to coordinate efforts, locate victims, and map affected areas, ensuring resources are deployed efficiently where they're needed most. First responders can quickly navigate through damaged infrastructure, and aid agencies can track supplies to ensure they reach vulnerable populations. Furthermore, GPS is an indispensable tool for scientific research across a vast spectrum of disciplines. Geologists use it to monitor subtle shifts in tectonic plates, predicting earthquakes and studying crustal deformation. Climate scientists employ GPS sensors to track glacier movement, measure sea level rise, and study atmospheric conditions. Ecologists outfit wildlife with miniature GPS trackers to study migration patterns, habitat use, and animal behavior, providing crucial insights for conservation efforts. From mapping the ocean floor to understanding the Earth's magnetic field, GPS data provides the foundational geospatial information that allows scientists to unravel the planet's most complex mysteries. It is a testament to its versatility, a quiet enabler of progress that, while rarely noticed, is fundamentally woven into the intricate tapestry of our modern, technologically advanced society. For all its unparalleled convenience and critical utility, the very brilliance of GPS harbors an inherent vulnerability, a digital Achilles heel that poses significant risks to our increasingly dependent world. A system built on delicate signals beamed from satellites over 20,000 kilometers away is, by its nature, fragile. Unlike the ancient mariner whose primary threat was the physical storm, our modern reliance faces a spectrum of invisible threats, both natural and man-made. One of the most immediate dangers is jamming. With relatively inexpensive and readily available equipment, a malicious actor can overwhelm GPS signals with localized radio interference. This doesn't destroy the satellites, but it blinds receivers within the jammed area, rendering them unable to acquire a fix. Imagine a truck driver losing their navigation in a critical urban intersection. Or worse, a commercial airliner having its precision landing systems compromised near an airport. While military-grade receivers have anti-jamming capabilities, civilian systems are far more susceptible, leaving vital infrastructure from shipping to agriculture exposed. Even more insidious is spoofing, where false GPS signals are broadcast, tricking receivers into thinking they are in a different location or time than they actually are. In 2017, hundreds of ships in the Black Sea reported their GPS units placing them miles inland, a suspected state-sponsored spoofing attack. Such an attack could misdirect ships, disorient autonomous vehicles, or even interfere with critical timing systems, with potentially catastrophic economic and safety implications. Beyond deliberate attacks, natural phenomena also pose a threat. Powerful solar flares erupting from the sun can unleash bursts of electromagnetic radiation that disrupt the Earth's ionosphere, scrambling satellite signals and causing widespread GPS outages. While rare, a severe solar storm could cripple global communications and navigation for days or even weeks. Finally, the growing threat of cyber attacks looms large. While the satellites themselves are robust, the ground control segments, the data links, and the receivers are all potential targets. A sophisticated cyber attack could degrade signal integrity, inject false data, or even incapacitate parts of the network, creating chaos. Our absolute dependence on GPS for everything from financial transactions to emergency services means that any significant disruption could trigger a cascading failure across multiple critical infrastructures. The ancient mariners' world was dangerous, but their vulnerabilities were visible and tangible. Ours, while seemingly more advanced, relies on an invisible foundation that, if compromised, could plunge us into a modern form of navigational darkness, reminding us that even the most wondrous technology has its weaknesses. In our quest for ultimate convenience, have we unwittingly traded vital skills for instant gratification? We stand at a unique juncture in human history, where the fundamental ability to orient ourselves, honed over millennia, is slowly, imperceptibly eroding. Modern GPS, with its infallible voice, has become the omnipresent guide, the digital crutch we lean on without question. This pervasive reliance has profound implications, not just for our practical capabilities, but for our very cognitive architecture. Studies are increasingly highlighting a decline in basic spatial awareness, the innate sense of direction that once allowed our ancestors to traverse continents with nothing but the sun and stars as their compass. We've become so accustomed to turn-by-turn directions that the intricate mental mapping once required to navigate unfamiliar territories now feels like a lost art. Consider the lost art of reading a paper map. Once a rite of passage, a skill demanding critical thinking, pattern recognition, and an understanding of scale and topography, it's now often viewed as an archaic chore. The simple act of unfolding a map, orienting it to your surroundings, and plotting a course engages different parts of the brain, fostering problem-solving abilities that are bypassed by the passive reception of GPS instructions. What happens when the signal drops, when the battery dies, when the grid fails? We become, quite literally, lost at sea, not on an ocean, but in a world we've come to expect will always tell us where we are. This isn't merely about inconvenience. It's about a diminishing resilience, a profound vulnerability introduced by our absolute faith in technology. The psychological impact extends beyond just getting from point A to point B. It affects our memory, our observational skills, and our engagement with the environment around us. We often drive through new cities, eyes fixed on a screen, missing the architectural nuances, the subtle street signs, the very essence of the place, because our guide has already told us where to look and when. This over-reliance, a silent epidemic, is the unseen cost of convenience, leaving us more connected to satellites, but paradoxically less connected to the world beneath our feet and the innate human capacity to explore it. After examining the staggering precision of modern GPS and contemplating the profound implications of our growing dependence, we arrive at the central question of our journey: who navigated the seas better, ancient stars or modern GPS? But before we attempt to answer, we must first confront the inherent slipperiness of the word better. It is, without doubt, a subjective term, a canvas onto which we project our own values and priorities. There is no single, unequivocal victor in this grand navigational contest, for better, profoundly, depends on the criteria we choose to apply. Are we defining better by pinpoint accuracy? In that realm, GPS stands as an undisputed titan. Its ability to place a ship, a car, or even a drone within a few meters of its precise location, anywhere on Earth, at any given moment, is a marvel of human ingenuity. No ancient mariner, no matter how skilled, could ever hope to achieve such granular precision across vast, featureless oceans. But what if our metric for better shifts to resilience, to self-sufficiency? Here, the balance begins to tilt. Ancient navigation, rooted in observation and embodied knowledge, was inherently resilient. It could not fail in the way a technological system can. There was no battery to drain, no signal to lose, no complex software to glitch. The stars, the sun, the waves, the winds. These cosmic guides were always present, always available, demanding only the human capacity to read them. This self-contained, unpowered system stands in stark contrast to the intricate, energy-intensive infrastructure required to maintain our global satellite constellation. Or perhaps, better, speaks to societal impact. Which system fosters a deeper understanding of our world, a more profound connection to the cosmos, or a greater sense of individual capability? One system democratizes access to navigation, but potentially at the cost of fundamental skill, while the other demands years of dedicated learning, but builds a deep, intrinsic understanding. The answer, then, is not a simple either-or, but a complex interplay of values. As we delve deeper, we must hold these varying criteria in our minds, understanding that the best form of navigation might not be a single solution, but a dynamic spectrum reflecting what humanity values most at any given time. The defining characteristic of modern GPS is its breathtaking accuracy. Imagine standing on a remote island in the vast Pacific, and with a small handheld device, knowing your precise longitude and latitude to within a few meters. This global reach, powered by constellations of satellites like the United States, Navstar GPS, or Europe's Galileo, orbiting 20,000 kilometers above the Earth, delivers an unprecedented level of precision. Since its full operability in 1995 for civilian use, GPS has transformed everything from aviation to agriculture, commerce to crisis management. It allows container ships to plot the most fuel-efficient routes across oceans, reducing transit times and costs, and guides search and rescue teams directly to those in distress. This level of exactitude was unimaginable, even a century ago, let alone millennia past. Yet, this incredible precision comes with an inherent trade-off, a dependence on an intricate, power-intensive, and potentially vulnerable global infrastructure. What happens when the satellites fail? What if a solar flare disrupts signals, or a cyber attack cripples the ground stations that maintain the system? History offers stark reminders of such vulnerabilities. In 2018, a glitch in Europe's Galileo system led to outages for several days, causing concern across industries. Military strategists are well aware of the potential for adversaries to jam or spoof GPS signals, rendering it useless. Contrast this with the robust, resilient, and utterly self-contained nature of ancient celestial navigation. A Polynesian navigator like Mau Piailug, who guided the Hokulea across thousands of miles of open ocean without instruments, carried his navigation system not in a device, but in his mind, his body, and his deep intuitive understanding of the natural world. His stars couldn't be jammed, his wave patterns couldn't be spoofed, his sun couldn't be turned off. This system, honed over thousands of years by cultures like the Vikings who used sunstones, or Arab navigators like Ahmad ibn Majid who mastered the Kamal, was independent of any external power source or complex technological infrastructure. It was a symbiotic relationship between human observation and the unchanging rhythms of the cosmos. The sacrifice was precision. Ancient navigators might land within a sea-mile of their target, not meters, but the gain was profound independence. Their journey might be slightly longer, but their arrival was virtually guaranteed, shielded from the very systemic failures that plague our technologically advanced age. This trade-off between absolute accuracy and unwavering resilience defines one of the core tensions in our navigational debate. One of the most profound differences between ancient and modern navigation lies in their respective demands on human intellect and effort. GPS offers unparalleled accessibility. From a child's first smartphone to an elderly traveler exploring new lands, anyone, anywhere, with a signal, can instantly access global positioning data. There is virtually no learning curve to using GPS. It democratizes navigation, empowering billions with the ability to find their way across unfamiliar terrains, transcending language barriers and educational disparities. This immediate, universal access has fostered a new era of global mobility, allowing us to venture further, faster, and with less anxiety than ever before. It's a tool that requires minimal personal investment, delivering maximum immediate utility, functioning as a true black box. We input a destination, and it provides the path, without needing to understand the complex mechanics beneath. Yet this accessibility comes at a hidden cost, a diminishing appreciation for the deep, embodied knowledge that once defined navigation. Ancient methods were not accessible in the same way. They demanded years, often decades, of dedicated observation, memorization, and practical experience. Think of the Micronesian navigators who began their training as children, learning to read swell patterns reflected from distant islands, interpreting the subtle nuances of cloud formations, memorizing thousands of stars and their rising and setting points across the horizon. This wasn't merely rote learning. It was an immersive, holistic education that integrated astronomy, meteorology, oceanography, and an almost poetic understanding of the natural world. It was a skill passed down through oral traditions, carefully guarded secrets, and intense apprenticeship, like that endured by master navigators such as Papamau Piailug, who spent his youth internalizing the wisdom of his ancestors on Satawal. This deep knowledge fostered not just the ability to navigate, but a profound connection to the environment. It built mental resilience, acute observational skills, and an intrinsic understanding of one's place within the vast cosmic tapestry. With GPS, we become passive recipients of information. With ancient navigation, we were active participants in a complex, living system. The contrast is stark: instant gratification versus profound wisdom. One provides answers with the push of a button. The other asks for a lifetime of dedication, rewarding it with an unparalleled understanding of the world, and indeed of oneself. Beyond the human skills and technological marvels, there lies a quieter, yet profoundly important dimension to our navigational comparison: the environmental footprint. When ancient mariners set sail, their impact on the planet was minimal. Their canoes, often crafted from sustainable materials, like wood and natural fibers, utilized the power of the wind and currents, requiring no fossil fuels. Navigation tools like the astrolabe, the camal, or even the simplest star chart were handcrafted, durable, and required no external power source. When a journey was complete, the kuru, waste, was biodegradable, returning to the earth from which it came. The carbon footprint of a Polynesian voyage across the Pacific, stretching back to 1000 AD, or a Viking longship traversing the North Atlantic in the 9th century, was negligible, almost entirely absorbed by the natural systems around them. Their relationship with the environment was one of integration, not exploitation. Now, let us consider the environmental cost of our modern navigational marvel. The global positioning system is not a benevolent, ethereal force. It is a vast, complex, and energy-intensive infrastructure. It begins with the launching of satellites, a process that involves powerful rockets, consuming tons of fuel and releasing significant greenhouse gases into the atmosphere. Each launch is a monumental event, not just in engineering, but in its environmental impact. Once in orbit, these constellations of satellites, like the 31 operational satellites of the Navstar GPS, must be continuously powered, monitored, and maintained from ground stations located across the globe. This requires constant energy consumption, often from non-renewable sources. Furthermore, the lifespan of a satellite is finite, typically 10 to 15 years. What happens then? They become space debris, a growing problem in Earth's orbit, posing collision risks to active satellites and future missions. And on the ground, the very devices we use, our smartphones, car navigation systems, and marine GPS units, contribute to the accelerating problem of electronic waste, or e-waste. These devices are packed with rare earth minerals, manufactured in energy-intensive processes, and often discarded after only a few years, polluting landfills with toxic materials. The digital convenience we crave comes at a very tangible planetary price, a stark contrast to the harmonious, almost invisible footprint of those who once navigated by the silent, eternal guides of the cosmos. The choice between stars and satellites is not just about finding our way, it's about the kind of world we choose to leave behind. Having explored the strengths and vulnerabilities of both ancient and modern navigational paradigms, a critical question emerges. Must we choose one over the other, or is there a smarter path forward? The future of navigation, increasingly, appears to lie not in an exclusive allegiance to either the stars or the satellites, but in a strategic, intelligent integration, a hybrid approach that leverages the best of both worlds. Imagine a world where advanced technology doesn't replace fundamental human skill, but augments it, where digital tools serve as powerful complements to a reawakened instinct for natural wayfinding. This hybrid future could manifest in countless ways. Consider a modern naval officer or a long-distance sailor equipped with the latest GPS, Galileo, or GLONASS systems for pinpoint accuracy, but also rigorously trained in celestial navigation, dead reckoning, and even traditional weather forecasting. In the event of a system failure, a cyber attack, a catastrophic solar storm, or simply a dead battery in a remote area, they wouldn't be lost. Their training in ancient methods would provide a crucial, resilient backup, a Plan B, rooted in the timeless rhythms of the cosmos. Modern maritime academies, recognizing this vulnerability, are already reinstating celestial navigation into their core curricula, not as a nostalgic nod to the past, but as an essential safeguard for the future. Beyond military and professional use, this hybridity could extend to everyday life. Picture smart devices that not only provide turn-by-turn directions, but also offer natural navigation cues, pointing to the sun's position, indicating the direction of prevailing winds, or highlighting prominent celestial bodies visible at night. Augmented reality applications could overlay constellations onto the night sky, helping users to identify stars and planets, fostering a renewed connection to the cosmos. This isn't about rejecting technology. It's about making technology smarter, more resilient, and more attuned to human capability. It's about building a navigational system that is robust against unforeseen challenges, a system where human intuition, honed by millennia of ancestral knowledge, can seamlessly integrate with the cutting-edge power of satellite networks. The goal is to cultivate a new generation of navigators who are both digitally literate and cosmically aware, creating a more adaptable, self-sufficient, and profoundly secure future for global exploration. As we race forward into a future dominated by digital navigation, we must pause and reflect on what might be irrevocably lost along the way. Beyond the practical skills and resilience, there's a deeper, more profound connection that is slowly fading from the human experience, our direct, intimate relationship with the cosmos. For millennia, the night sky was humanity's first map, its first clock, its first calendar, and perhaps its first sacred text. The stars were not merely points of light. They were guides, storytellers, and a constant reminder of our place within a vast, awe-inspiring universe. Ancient mariners, gazing up at the Milky Way stretching across the inky blackness, felt a primal wonder, a direct engagement with the forces that governed their world and their journeys. This connection fostered a sense of humility, curiosity, and an almost spiritual understanding of natural patterns. The rising of Orion, the setting of the Pleiades, these celestial movements dictated planting seasons, migration paths, and the very rhythm of life. Polynesian navigators, often described as star readers, possessed not just technical skill, but a poetic understanding of the star compass, where each star marked a crucial direction, interwoven with ancestral knowledge and myth. This was more than just navigation. It was a way of being, a philosophical framework that bound humans to the heavens and the earth. Today, illuminated by the pervasive glow of urban sprawl, and increasingly reliant on the invisible signals from space, many of us rarely look up. The night sky has become a blurry, light-polluted canvas, the stars obscured, their ancient wisdom rendered mute. We navigate by an abstract grid of coordinates, a voice in our pocket, losing the physical and emotional engagement with the real world around us. What is lost is not just a skill, but a sense of wonder, a diminished appreciation for the intricate beauty of the natural world, and a profound disconnection from the grand cosmic narrative that once shaped human civilization. The silent shift from looking up to looking down, from observing the infinite to following a glowing dot, carries an unseen cost, a loss of ancient wisdom, a diminishment of our sense of place, and perhaps a quiet erosion of the very spirit of human awe. As our journey through the annals of navigation draws to a close, from the primal wisdom of the stars to the sophisticated embrace of satellite technology, one truth remains constant, shining as brightly as the North Star itself, the indomitable human spirit of exploration. Regardless of the tools at our disposal, whether a carved wooden stick chart or a hyper-advanced GPS receiver, the fundamental human need to know where we are and where we are going persists. It is this innate curiosity, this yearning for the horizon, that has propelled us across oceans, over mountains, and ultimately into the vast expanse of space. From the audacious voyages of Polynesian navigators who colonized vast stretches of the Pacific, relying on their profound understanding of waves, birds, and stars, to the Vikings who braved the treacherous North Atlantic to reach new lands like Greenland and North America, humanity has always been driven by an insatiable desire to push boundaries. This same spirit fueled the age of exploration, guiding caravels and galleons across uncharted waters, and it continues to power our modern endeavors, from deep-sea submersibles mapping the ocean floor to Mars rovers seeking signs of life on another planet. The methodology changes, the technology evolves, but the underlying drive remains unaltered. Navigation, in its deepest sense, is not just about finding a physical location. It's about charting a course through the unknown, both external and internal. It's about overcoming fear, embracing challenge, and expanding the very definition of what is possible. GPS may tell us precisely where we are, but the stars still beckon with questions of infinite possibility. The marvel of a global satellite network, a testament to collective human genius, is itself a product of this enduring quest for knowledge and discovery. And as we look to the future, perhaps blending ancient wisdom with cutting-edge innovation, we realize that the true legacy of navigation is not found in the tools themselves, but in the enduring, unquenchable human desire to explore, to understand, and to constantly seek new horizons. It is this spirit that will continue to inspire new inventions, new journeys, and new understandings of our place in the universe for all eternity. As our extraordinary journey through the epochs of navigation concludes, the profound question of who did it better reveals itself not as a simple choice, but as a testament to two distinct pinnacles of human achievement. Ancient mariners, guided by the silent ballet of the stars and the nuanced language of the ocean, cultivated a navigation system rooted in unparalleled human skill, memory, and an almost spiritual connection to the natural world. Their methods demanded deep resilience, acute observation, and a holistic understanding of their environment, fostering a self-reliance that modern technology cannot replicate. They navigated not just with instruments, but with their very soul. In stark contrast, modern GPS represents a triumph of engineering and global connectivity. Its breathtaking accuracy, instantaneous data, and universal accessibility have revolutionized maritime travel, trade, and safety, making the vast oceans less perilous and opening up possibilities our ancestors could only dream of. It is a system built on logic, precision, and an intricate web of digital whispers across the globe. Both stand as monumental achievements, born of humanity's ceaseless drive to explore and understand our place in the world. The wisdom of the past and the wonders of the present each hold invaluable lessons. Perhaps the ultimate mastery lies not in choosing one over the other, but in a harmonious blend. As we continue to chart unknown waters, the future of navigation may well embrace the marvels of technology while preserving the profound knowledge, the deep connection to the cosmos, and the sheer human ingenuity that our ancestors so brilliantly mastered. For only then can we truly ensure we never lose our way, not just on the seas but in our understanding of ourselves.